All right, number 16. This one's pretty similar to number 15. What is the chemical formula for calcium sulfate? And so we were combining calcium and sulfur in the previous problem. Here we're combining calcium and sulfate, SO4. Now, I would really encourage you to lock into your memory that ending of the word right there, ATE, that should trigger you to look to your list of polyatomic ions. That is, lots of things on this list end with ATE. So it's a big, bad mistake to confuse sulfate for sulfide, which is S from the periodic table. And I don't know, so much of what we've done this year has depended on your ability to recognize the difference between sulfate and sulfide, or nitrate or nitride, or phosphate or phosphide. The ATE, that should tell you polyatomic ion. So we are just going to examine the oxidation states of these two things. Calcium +2, just like it was here, and sulfate comes from the -2 group here. Where is it? There it is, sulfate, SO4, -2. And so just like in the problem before, we've got matching oxidation states. Oh, whoops, this is not positive. This is -2, excuse me. +2 and -2, they cancel each other out, and our formula is CaSO4. Okay. All righty, 17. Okay. All right, let's take some time with this one. Number 17. This here is the structure for phosphoric acid, and it is incorrectly drawn. So it looks right at first sight, but it's not right. We'll talk about why. If the central atom comes from the third row of elements, like phosphorus does, and what I'm saying there is that, like, here's our periodic table, and most of the molecules that we drew Lewis dot diagram structures for, or Lewis structures, the central atom was in the second row. It was carbon, nitrogen, or oxygen. Typically, those were the atoms that we used as our central atom. And we learned that rule just great, where we're trying to fill the octet around all the atoms and whatnot. Things get a little complicated for the central atom as you go below the second level. And phosphorus is the atom we're talking about in this problem. So this is where the octet rule sort of turns more like into the octet guideline, because you're going to see that phosphorus, when it's correctly drawn into a molecule as a central atom, it does not have an octet, but it's okay. There's just a different rule that you follow when you get to central atoms below the second level of atoms on the periodic table. So here's what that looks like. And it's important that you understand what phosphorus as a Lewis dot diagram looks like. So remember that phosphorus, when you look at its valence structure, has 5 valence electrons. That's why typically this would like to make 3 single covalent bonds to satisfy the octet. But that's not totally how phosphorus works. So I'm going to show you how this is drawn, and then explain it. So it's mostly right. This is actually mostly right. So I'm just going to reproduce this here. Oh crap! And then there's an H here. There we go. Okay. So this is all good. This is all good. This is all good. Here's the issue though. As it's written now, phosphorus has an octet, which you might think is a really good thing, and that's always been the case for us. But phosphorus needs to have as many bonds around it as it's got electrons in its Lewis dot diagram. And that's what that means is that because there are 5 electrons in the Lewis dot diagram, we need to match that with 5 bonds around phosphorus. So to do that, if you look at how we can make that happen, we are going to poach a set of electrons from this uppermost oxygen, and we're going to turn those electrons into a second covalent bond, a coordinate covalent bond. And we're going to leave the other sets of electrons present on that upper oxygen. And so oxygen still has an octet because we can count the 4 electrons and the 4 electrons that are in the 2 bonds. Those all belong to oxygen. Phosphorus, though, if you're thinking about this, you're probably like, that's not right, because now phosphorus actually has 10 electrons around it instead of a stable octet that we've always learned is kind of the what we're shooting for. But like I said, guys, the octet, it's more of a guideline than it is a rule. So this is actually the way that phosphorus looks as a central atom. It's got 5 bonds around it, which is a little bit goofy. So we can talk more about this one, but that's how it should look. Okay. All right, 18. 18. What is the bond angle? HOH in a water molecule. So when you've been given HOH, that just means we're looking at a hydrogen and we're going to an oxygen and another hydrogen. So we're just studying this angle here between the hydrogen to the oxygen to hydrogen. What is that bond angle? And it's important to remember that this is where this idea of VSEPR comes in, the valence shell electron pair repulsion theory, which basically shapes the geometry of the molecule by the repulsive forces that occur between these pairs of electrons and the bonds, which are electrons. And so here, I want to make sure that you can see this really well. We've got our central atom of oxygen. We've got a bond here, here, and then we've got these electrons here and here. That is 4 areas of what we call electron density, right? So electron densities are just, they're places where the electron pairs are, or there's a covalent bond. And when we have 4 densities of electrons, then they try to fight for as much real estate as they can get around that central atom. And on paper, that usually looks like 90 degrees. That would be like if A was our central atom, and then we've got as spread out as far as we can go these X's. So on a flat surface, we would say that this is a 90-degree bond angle, X to A to X. But in 3 dimensions, you can imagine how these things can find a little bit more space for themselves. And so it turns out that these guys orient themselves more like this, into about 104-degree bond angle. And that has to do like this, where we've got, remember when we drew it this way? Where we drew a number of molecules that looked like this. This was the tetrahedral arrangement around the central atom. And water has a tetrahedral arrangement, even though we would consider this to be a bent molecule. But, you know, if you just imagine that these are electrons rather than bonded atoms, then you can see how that geometry still works there. And this bond angle is about 104 degrees. Okay. Other ones that you might see, like if we had something like boron trifluoride, for example, this would be a 120-degree bond angle. Or something like CO2, this is a 180-degree bond angle. And I'm trying to think of the other. Oh yeah, like the trigonal planar, like this. or excuse me, trigonal pyramid like this. This still has 4 areas of electron density, so this is about 104 as well. But anyway, we can brush up on those bond angles. All right, number 19. These are just some simple diagrams that are trying to represent either atoms that would be part of an element, or more complicated structures that would be compounds, or a mixture of certain things. So let's just label these as element, compounds, or mixtures. I'm going to call this an element. And sorry, here they sort of are like this, that, and then, sorry. So I think this first one is an element. I mean, the structures are all identical to each other. They're all very simple. I would say that these are probably atoms of the same element. Okay. These guys, you could probably make the same argument. They're pretty simple structures, except that we've got kind of, instead of just one type of shape, we've actually got like 2 types of shapes, right? I think if I were forced into it, I would probably call this a compound, where we might have different atoms, like triangle atoms bonded to circle atoms or something like that. And so I would probably call that a compound. This one I would call probably a mixture. I'd probably say this is like a mixture of elements, like different types of atoms are mixed together but not bonded together. And here I would say maybe this is another mixture. Maybe this is a mixture of compounds, or it could be a mixture of elements and compounds or something like that. But still, we've got 2 very different types of things that are mixed together here. So that goes back to some stuff we did all the way back in Unit 1. And number 20. Which phase of matter has the highest ability to be compressed? So here we're talking about either solids, liquids, or gases. You may, in some cases, you may hear of plasma. Just forget about plasma. We don't care about it. So disregard plasma in every sense that you would ever see it. Remember that the ability to be compressed has to do with the amount of space that is between the particles of the substance. So if I was looking at a solid substance, I might think of those particles, atoms, I guess you would say, as being very, very, very tightly packed. And there's not really much room for them to compress much more than they already are, so they're not very compressible. Liquids, the particles are farther apart from each other than they are in a solid. But a characteristic of liquid is that they're just not that compressible, maybe to a certain degree, but not very much. Gases, on the other hand, one of their major characteristics is that the particles are so far apart from each other that they're highly compressible. You can squeeze a whole bunch of gas into a very, very small volume. So which phase of matter has the highest ability to be compressed? Gases, for sure. Okay.